Okay, good morning and welcome to our class today. Since there are still a few students showing up within the next couple of minutes, I guess, I'll just quickly repeat what we did in our last class. And then I have two questions I would like to ask you regarding our classes next week. And then we will continue our class. So I'll share the screen. Let's have a look at the script. Okay, so what did we do so far? We started talking about kinetics of a point mass, and the simplest form of motion, the rectilinear motion. So we said, okay, we need three variables to describe a rectilinear motion: the position, velocity, and acceleration. And we discussed how to compute these three variables and how they depend on each other. Then we did the same for the circular motion. Circular motion of a point mass. It's quite similar to the rectilinear motion. We need three variables to describe the motion: angle, angular velocity, and angular acceleration. And the relation between these three variables is similar to the rectilinear motion. Then last thing we discussed was the additional parameters, the first few additional parameters we need to compute our different variables and how to change from one motion to the other, from rectilinear motion to circular motion. So we already discussed the number of rotations, the rotational frequency, and the arc length. And this is where we will continue today. So we're 77 now. I think that's good enough for today. So before we continue on the next page of our script, there are two questions I would like to ask. Because Monday next week, we have two classes, one online, one on campus, offline. So to make sure that our room is big enough for all of us that attend the offline class, I would like to know more or less how many students will attend the on-campus class. That's the first question. I'll just post the question such that you can reply to it. And the second question is, for the students who attend the offline class, how many of you still need class materials? So how many lecture notes, exercise books, etc. should I bring to class? Okay, so I will start the questionnaire, and please answer offline or online, and you need class materials or not. Just for me to know, is our room big enough? Do I have to look for a different room? And how many lecture notes do I need to bring to class?
Yes.
So I have 66 answers, 67 answers so far. We are 85, so maybe we can reach 80 answers at least. Okay, 47 answers. There's still some. Oh, okay. There's. I'm coming to. Yeah, please answer with offline if you will attend the offline class from October 22nd. Okay. We have 77 answers so far. Nobody else wants to answer. I will close. '79. Well, to the students who just showed up right now, I think you should see the 2 questions as well. If not, then just let me know, just a short information in the chat. 2 questions. First one, will you participate in offline or online classes? And do you still need the lecture notes printed out? So, because I will prove if our room is big enough, and I will decide how many lecture notes I have to bring to class on Monday. Who's not here in Schweinfurt can print it as well. Yes, only on Mondays. Friday is an online course. Okay, well, we have 82 answers out of 91. So I think I will stop right here. Okay, just if you want to see it as well. So we have 46, just quickly taking notes for offline, and 30 who still need class materials. Okay, great, thank you. I will send an email via e-learning to let you know in which room we will have our class on Monday. This will be the room for throughout the whole semester. I don't know which one is written in your schedule right now. And then, yeah, I will just, on Monday, our class is at 2:15. So I think by 11, you should have an email where I tell you which room we will meet. Okay, thanks for participating. Then let's get back to our which room to all. Yeah, just a second. No, I was not talking about making this lecture earlier today. I've never said that. So maybe somebody else, but it wasn't me. Which room to all the students? Is that a question? Well, on Monday, I will send you an email telling you which room we will meet. Of course, only for the offline students. Everybody else who participates online, doesn't matter where you are, of course. Offline class is at 2:15 on Mondays. Yes, I will send an email. Okay. Yes? Question? No. Okay. 5103. Yeah, this room is probably not big enough, and that's why we have to change the room. Okay. But thanks. Yeah, 5103 is your room. So it will not be in this room because now 46 students said that they will attend offline class, and I think this room is only 30 or 35 seats. So we have to change, but I will organize that until Monday. Yes, you should be expecting an email from me on Monday at 11 or earlier. Okay. Okay, now let's get started. So there's still 2 more variables we have to discuss. So the first one is the velocity, because on Monday I told you, okay, we have our different variables for rectilinear and circular motion. And in case of circular motion, we're describing the angular velocity. And now we want to compute the velocity itself from angular velocity. And for this, we can use this relation stated here. We have the velocity, which is the time derivative of the position, ds over dt. And we already know from the previous page that the position or distance traveled is equal to r times d phi, the arc length. The distance traveled along a circular path corresponds to the arc length. Here, I'll just state it here. Arc length. And the time derivative of this angle is the angular velocity. That's what we already learned in our last class. And in consequence, the velocity vector itself can be computed by radius multiplied by angular velocity omega t. And the direction of this velocity is always perpendicular to the radius of our circular path. So let's do the small figure again, which we had on our previous page. So that's our that's the center of the circular path. That's the radius, and this is our arc length. The distance traveled from t0 to t, for example, or some time t. Then here we have a velocity vector perpendicular to the radius, tangential on the path. Velocity at time t. And then later on, the position of our point mass changes. And then this would be the direction of our velocity vector at time t plus dt, dt meaning a little bit later in time. So however big the time interval is. Okay, now our last variable is the acceleration. In general, the acceleration is the time derivative of the velocity. But now for our point mass moving along a circular path, there are two types of change in motion. If you have a look at the velocity vector in our figure that we just did here, our velocity vector changes in direction, and if our point mass is accelerated, it changes in magnitude. The size of the velocity changes can increase or decrease. So we have to consider both changes, change in magnitude and change in direction. So let's have a look at the first one. Yes?
I'm sorry. So that's why we added the dt at the edge, because there is a changing direction. And
no, this dt means that it's later in time. Dt is a small time interval.
So it's a change in time?
Yeah, it means that at time t, or could be just writing here, could be time t1 and this could be time t2. Okay. So first our point mass is here, and sometime later in time, then the point mass is there. So from position 1 to position 2, our point mass has moved over there, and dt simply refers to a small change in time, a small time interval. Okay?
Okay, thank you.
The point mass moves along a circular path, and that's why the velocity vector changes as well in magnitude and direction.
Excuse me, Professor?
Yes.
I have a question. So when we're talking about VT, we're talking about, let's just say, tangential velocity?
There's only a tangential. The velocity of a circular motion is always tangential on the path. There is no other velocity.
The thing is, like, I remember something doing in high school. We used to have an angular velocity and a tangential. I'm not quite sure if it applies.
A normal and tangential, not for the velocity, but for the acceleration. But that's what I will tell you in just a few minutes.
Okay, so just to be clear.
Yeah, no, it's not velocities. Velocity of a circular motion is always tangential on the path, but it's different for accelerations.
Okay, I'm asking this because on the previous slide we did an angular velocity. So, I mean, so on the diagram, there's not going to be a direction of an angular velocity or something.
Oh, the angular velocity is omega. Okay.
Yes, yes. So how would
but
you show
here
that?
I'm talking about the angular velocity has no specific point of action. Okay.
Okay. So,
the angular velocity would just be like this, omega. It moves. It's a rotation. It's a rotational velocity.
Okay, so the v is in meters per second, and this one is in radians per second or something.
Exactly.
Understood. Okay, thank you.
Yep, you're welcome. Okay, now let's get back to the change in magnitude of the velocity. Let's have a look at that. Now our velocity, or our small change of the velocity, can be written like this, dv. This d always refers to the change of the specific variable velocity in this case. The change of magnitude is always measured tangential on the path, since our velocity vector is tangential on the path. So the change in magnitude, if you remember Engineering Mechanics 1, simply refers to a change in the length of the vector. Okay? So the change in tangential direction. And we know the velocity, that's what we just stated above, is r times omega, radius times angular velocity. To make it easier to read, I'm just not writing this dependent on time. Okay, but of course we know velocity and angular velocity are time-dependent variables, but it's easier to read for you if we don't keep writing this all the time, because the equations will become very long. So now let's build the time derivative. The time derivative of the acceleration of the velocity corresponds to the acceleration. And since we are only discussing the change tangential to our path, it's a tangential acceleration. I'll just refer to the question in the chat in a minute, okay? Because you're just a bit ahead of of what we're talking about right now. Okay, now let's build the time derivative. Now we substitute the velocity by r times omega. Since we're moving along a circular path, our radius is constant, and we only have to build the time derivative of the angular velocity, which is equal to the angular acceleration, alpha. Okay, now this is our first equation for the acceleration. We have a tangential acceleration now I will write the dependent on time since this is our final equation. A is equal to R times alpha. And as the indice indicates already, the direction is tangential on the path. Same as the velocity vector. Okay, but now our velocity doesn't only change in magnitude, it also changes in direction, since our point mass moves along the circular path. And we have to consider this change as well. Now this is a change. Alpha is the angular acceleration. We wrote this on the previous page. Angular acceleration. Now again, we are considering a small change as stated in the figure above. And now if we consider the change in direction, the orientation of our vector changes. Okay, so it's the normal direction that changes.
I'm sorry, Professor.
Yes.
Because the direction of V is changing in a circular motion, we can never say that the velocity is constant in a circular motion. We can never say it's constant.
Well, the velocity itself can be constant in a circular motion, but the acceleration is not.
But how if we're changing direction, so the velocity is not the same because of the direction?
No, as long as the object moves, it needs to have a velocity. And if it moves with constant angular velocity, the velocity itself is also constant, but the orientation of the velocity vector changes. So this is the orientation, the direction is never constant. That changes over time. I will just let me finish this part, and then we will draw a figure, and then it might be easier to understand. Okay? Then I will discuss that when can it be constant or zero or whatever. Okay. So we have the velocity itself, and we also have to consider the change in magnitude. Since we're only considering a small time interval, it's this change dVt as stated above. And then it changes dependent on the angle, dependent on the position. Now, we can neglect the dVt, the change in magnitude, since this component is significantly smaller than the velocity vector itself. Okay, we start with our velocity vt, and then it changes a little bit. So this small change is much smaller than the velocity itself. Now we do the same as above. We build the time derivative. dvn over dt, which corresponds to our normal acceleration, is the velocity itself, and then d phi dt. Well, I always just said I will not write the time-dependent stuff, but okay. Then we end up with velocity times angular velocity. And this leads to our normal acceleration, a n t. Is we can substitute the velocity itself, as stated above in the orange box, by r times omega, and this results into r times omega square. Or we could substitute omega, and then it would result into v square over r. So what we say, we have a change, just repeating quickly, we have a change in direction since our position of the point mass changes and the velocity vector is always constant, is always tangential on the path, perpendicular to the radius. Then we have a change of the velocity vector itself, dependent on the angle due to the small change in the angle, d phi. And of course, our vector
Professor,
can change
sorry,
in
but
magnitude.
I have a question.
No, just let me answer the question in the chat first. The magnitude, and then there's also the small change dvt. But since the small change due to the change in length and magnitude of the vector is significantly smaller than the velocity itself, we can neglect that part. And then we just build the time derivative to obtain the accelerations. Okay, now, other question.
Professor, when you write dvt, right, like that, is it the same as writing like this?
I don't know. What is the second type of writing for you?
Like, it's like this, just the, like normally you write, like let's say ax and ay. Just like saying that this a in reference to this. So this is just a reference to this one.
No, that's no. If I write a index tangential, for example, then I refer to the acceleration in tangential direction. Or if I would write something like this, then I would refer to the acceleration in x direction. But if I write like this, then I mean a is time dependent. So there's a different acceleration depending on the time. So I could say a at time t equals 0 is something, or a at time t equal 2 seconds is equal to something.
Ah, okay. All right. Thank you, Professor.
Yeah.
Ma'am, I have a question.
Yes.
For the change in direction of v, you said that we can neglect the dvt because it is very small, but how small can the value of dvt can be?
I'm not sure if I understood your question correctly. You refer to this.
No, dvt.
dvt.
Yeah, this one.
Above here.
No, the one in the change in direction.
Change in direction. Oh, this one. Yeah, that's the green text I wrote.
Yeah, you said that we can neglect it because it is very small.
Yes. Okay. If this is my velocity vector.
So how small can it be?
Vt. And now a little bit later, a minimal time interval later, it may have changed. dv tangential. So this green vector is significantly smaller than the red one, and that's why we can neglect it. That's what I'm referring at.
Professor, I have a question.
just in the chat, the change of the velocity, does it remain constant? The change in velocity, in tangential velocity, only stays constant if we have a constant angular acceleration. But just let me draw the figure. I need 2 more lines, and then we will draw a figure, and we will discuss that. It will be easier to understand, I think. There was another question.
Yeah, I have a question, Professor. Here, is this a phi or an alpha?
A phi.
That's
An
a
alpha
phi?
is looks like this. That's different, totally different, and that's a phi.
Right. Yeah, I just got confused. Thank you.
Okay.
Professor, why did we remove the dv over here? That's a green modification.
Because I said it's significantly smaller.
So we can always neglect it?
Yes. We will always neglect that. And actually for us, the relevant equations are the yellow equations. These are also stated in the formulary. Okay, I'm just telling you where they come from. So you do not have to do the math every time for every single problem because it's the same for every problem. You just have to do it once to understand, and then we can apply it to all the similar problems, point mass problems. Okay, so now we still need the direction. So as the name says, it's normal and points towards the center of the circular path. And then once we computed normal and tangential acceleration, we can build or can compute the absolute acceleration. So AT square plus AN square. And now we will draw a simple figure. Our circular path, whoops, not purple. So just let's go like this. So this is our circular path, and we have a point mass moving along this path. Here's our center. And now let's assume that our point mass is right here at some point in time. Okay. So this is our radius of the circle. Now what I will do, and what I will do here right now, I will use green for velocities and purple for the acceleration, just to have it easier to distinguish. That's an N, and please don't write into my notes. Tangential and normal, that's what we are talking about all the time. Okay, and what we stated above. Okay, now our acceleration, angular acceleration, points like this. We're just assuming this direction, okay? And our angular velocity points in the same direction. Now, we said that the velocity can be derived knowing angular velocity and radius, and it points tangential on the path, perpendicular to the radius. So this is our velocity vector, which can be computed by r times omega. And for the acceleration, we have to distinguish between tangential and normal component. The tangential component also points perpendicular to the radius, tangential on the path in the same direction as the velocity vector. I'm just adding it above. And this is AT, which is equal to R times alpha. And the normal component of the acceleration points in normal direction towards the center of the circular path. So this way. And this is a normal, which is equal to R omega square. These are the three vectors we have to memorize for point mass in circular motion. Now, as long as our point mass moves, it has an angular velocity, and the velocity vector is not zero. If the point mass moves with constant angular velocity, omega is constant, then the angular acceleration is zero. We discussed this relation on Monday already. If omega is constant, alpha is zero. If alpha, the angular acceleration, is zero, then the tangential component of the acceleration, AT, is zero. And there's only a normal acceleration, AN, acceleration towards the center of the circle, the circular path. That's one special case. In general, we always assume our object, our point mass, is accelerated and has a velocity. Yes, the absolute acceleration, it's just a vector sum, same as in statics, engineering mechanics 1, where you had vector in x direction and vector in y direction, and both the resultant, it's the same here. The vector sum of these two vectors and the angle.
So, Professor, what is the special case again?
First special case is it moves with constant angular velocity. Option 1. Omega unequals 0, alpha unequals 0. So all three vectors exist. We have V, AT, and AN. Option 2. Omega is constant. Oops, sorry, German. Constant. In consequence, alpha is 0. Time derivative of a constant value is 0. If alpha is 0, we have velocity and a normal acceleration, but tangential acceleration is equal to 0. Third option.
All three of them, or what? All three of them equal to 0? V, AN. Oh.
V and AN exist, but AT is equal to 0. Option 3. Omega is 0, but alpha exists. If our point mass is at standstill and we start the motion, the point mass has to be accelerated. And at the very beginning of this motion, the point mass is not moving, has no velocity, but it already has an acceleration. Otherwise, objects would never be able to change motion, start to move. So in consequence, the velocity and the normal acceleration are 0, and the tangential acceleration exists as not 0.
Professor,
Yes?
what's the difference between the angular acceleration and the tangential acceleration and the normal acceleration?
The angular acceleration is independent of the position. We have the same angular acceleration everywhere on our path. So it doesn't matter whether the point mass is here or wherever, which point we want to describe. It's always the same because it states radians per square second. And tangential and normal acceleration are dependent on the path, on the position of our object, meter per square second.
Professor. So
Yes?
may I? Yes. So basically, the normal component of the acceleration can appear also on a curved path, not only in circular motion.
No, of course. This is our simple form of motion. We are not yet discussing more complex types of motion. But of course, tangential and normal acceleration do appear on a path like this as well.
Thank you.
Yep. Okay, let's.
I have a question. So,
Alpha is still. If you do not remember, just I have a question. What is alpha again? Just if you go one page back, it's stated there. Okay, just don't ask me all the time. Alpha is the angular acceleration, but it's written in your documents. Another question.
yeah. So is the AN, the normal acceleration, could it be also outwards, or is it always towards the center?
No, always towards the center.
And does it have something to do with that centripetal force, or?
Yes, exactly. When we come to the forces, we will discuss this as well. But it keeps the point mass on the path.
Oh, okay. All right.
Yeah.
Thank you.
Yeah.
Professor, I have a question.
Yes.
How is dVn equal to Vt times d phi? Like at the when you wrote about change in direction of V.
How is?
dVn equal to Vt times d phi. Like where did we get the formula from?
Oh, that's our arc length equation. Remember we said, and now it's just we have the distance itself. Wait, where is it stated here? Is radius times the angle, and now we simply put the time derivative, and then we say, okay, the velocity, the change in direction of the velocity is the velocity itself multiplied by the angle. Up here we have here it's stated arc length.
Yeah, we have Vt is equal to r
S
times
and R, right?
d phi. Yeah.
And now we do the same simply by building the time derivative of this. And the time derivative of S is the velocity, and of R is, in our case, the velocity as well, just the specific velocity. But this equation is still true because we built the time derivative on both sides. dV n is equal to, V plus the small part. And then the d phi from here.
But isn't r a constant?
Well, yeah, r here is a constant because it's the radius of the path, and for our case, the velocity itself is also a constant velocity in this time, plus this small change in time, but this small change in time is also a constant value.
Yeah, but my question is like, if R is a constant, then how can we differentiate it to get V?
It's it's a mathematical thing. We do the kinematic conditions later on, and they just state that if you have a relation for the positions, for example, this relation between the positions is also true for the time derivative of these variables. So they might be constant, yeah, but in the time derivative of both sides, they're still constant and the relation is still true. It's a bit difficult. We will discuss this in a few weeks. I'm not quite 2 or 3 weeks probably. Later on, we will have equations like this. X is equal to, R times phi, for example. Okay, and even though our radius will then still be constant, we will say, okay, if this is true, then we can build the time derivative, and the velocity is equal to the time derivative on the other side. I think it's we will discuss this. Of course, it goes too far right now. Okay. Discuss this later again. Okay. Just let me see. There seem to be some questions. The normal acceleration. Yes, exactly. Yeah, thank you. There, somebody already answered. Oh, okay, you have. Okay, yeah. So the accelerations itself, of course, it keeps the point mass on the path, but it's the forces resulting from these accelerations. Okay, but for us right now, at the beginning of this class, we are only talking about accelerations and velocities, and not yet about forces. Okay, let's have a look at the small exercise from your exercise book, the very first problem, exercise 1.1. Okay. So, what situation do we have? Into a drill hole with a depth of 100 meters, and it is asked for the time that passes until the impact can be heard. Air resistance is negligible, speed of sound is given, and the gravitational constant is given as well. So what situation do we have? We have this drill hole. And we have a stone right here. The drill hole has a depth of 100 meters. So this variable here, gravitational constant and speed of sound. And we want to find the time. So now this stone is being dropped, and then it reaches the bottom. So this will take some time. And then it's already, we have the sound waves moving back up. And the question is, when can the sound be heard on top of the drill hole? And now we can use these equations that we already talked about on Monday, that are stated in our formulary. relations between distance traveled, velocity needed, etc. First one, our gravitational constant is constant, of course. Our gravitational acceleration is constant. So the velocity can be computed by g times t, our time. And our distance, in general, can be computed by x0 plus and the integral of velocity over time. So at the beginning of our motion, our stone has not traveled any distance yet. So x0 is 0. And we can build the integral of g times t, which results into 1/2 g t squared. Now we know that the stone travels a distance of 100 meters until it reaches the bottom. Then the time until impact can be obtained by rearranging the equation. So that's 4.515 seconds. The speed of sound is a constant value. So Vs is constant. In case of a constant velocity, the acceleration is 0, and the distance can be obtained by Vs times t. Now, again, the sound wave has to travel 100 meters. We can rearrange for the time and obtain 0.294 seconds. Then the total time, simply the sum of t impact and t sound. And then we obtain 4.809 seconds. Okay, that's a really simple exercise to start with, getting used to applying the equations that we have. And again, you do not have to memorize the equations. You simply have to find them in the formulary and apply them correctly. Okay? Let's just have a quick look at the formulary. So here, first part, rectilinear motion, that's what we just did. The relations between distance, velocity, and acceleration, then below the relations for the circular motion, and then here the relations that we just derived: tangential acceleration, normal acceleration, velocity, arc length. Okay, there are no questions. We will do a second exercise, exercise 1.4. And here we have a car that accelerates constantly in a plane curve. Radius is given, the time is given, and it accelerates from 54 kilometers per hour to 72 kilometers per hour. And we are asked to find the angular acceleration and the angle that is covered within this 10-second time interval. And the last question is which distance has been driven by the car, and how big is the acceleration once the car reached the 72 kilometers per hour. So now our car is our point mass performing a circular motion, and then we can apply the equations for the circular motion to solve this problem, and we can and after that we can compute the distance, which refers to the arc length, and normal and tangential acceleration to find the absolute acceleration of the car. Okay, I will give you a few minutes of time to solve this problem on your own, and then we will discuss the solution. Just about 10 minutes. And of course, if you have any questions, you can ask them before. On the last few pages of your exercise book, there are short solutions. So if you already obtained your results, your solutions, you can check your solutions with the exercise book. Okay. Okay, I think I will show you the solution. What do we have? We have a simple motion again. It's a circular, pure circular motion. Our point mass, the car moving through a curve, and we know it accelerates constantly. So it's a constant acceleration, and we can derive our velocity, our state, our equation for the velocity v1 is v0 plus a times t. We know velocities v1 and v0. We do know the time, and then we can derive the acceleration v1 minus v0 over time. And from that, we can find the angular acceleration alpha by a over r v1 minus v0 t times r, and that results into 2 times 10 to the power of minus 3 per square second. Okay. Then, and of course, if you have computed a here already, then this would be your tangential acceleration. So we can say, oh, well, we'll do the accelerations. First, we go in order of the question. So for alpha being constant, we can state the equation for the angle. Phi is equal to phi 0 plus omega 0 times t plus 1/2 a alpha t square. The initial angle is 0. We are not interested in the initial angle since we have to measure the angle during this 10-second time interval, so from starting position to end position. And then we can compute the angle omega times t, omega 0 times t is the same as v0 over r times t plus, and then we can substitute alpha, or we can just use the value that we just computed. If we substitute it, we have v1 minus v0 over 2r times t, and we obtain 0.7 radians, and then we can compute degrees from that. It's 40.1 degrees. So the car is covered an angle of 40.1 degrees. Okay, then the third question was the distance that has been driven by the car. The distance corresponds to the arc length, and once we know the angle, it's quite simple, r times phi, which is 175 meter. And last question, how big is the acceleration once the 72 kilometers per hour are reached? And here for the acceleration, we have to distinguish between tangential and normal acceleration first, and then we can build the absolute acceleration. So AT would be r times alpha, 0.5 meter per square second. Then A normal is v1 square over r, omega times r, omega square times r, or v1 square over r, which is 1.6 meter per square second. And from that, we can find the absolute acceleration which is 1.68 meter per square second. Okay.
Excuse me, Professor.
Yes.
In your first solution, the first answer, 2 into 10 raised to the power minus 3, is it 7.2 or just 2?
That's it. No, it's 2. Just 2.
Because the thing is, like, I'm getting the same answers as you, but I got a 7.2.
You have to change from kilometers per hour to meter per second for the velocities. Did you do that?
Okay. No. Okay.
No. Okay. Yeah.
Thank you.
Yeah, you're welcome. So, for example, for the V0, 54 kilometers per hour, that has to be computed into meter per second, and I'll just actually didn't state it here. Just have to do that real quick. So it's 54 times 1,000. 15 meter per second.
Excuse me, Professor.
Yes.
For the normal acceleration, why are we taking only the v1 square? What about the v0?
Because it's asked for the acceleration once we reach the 72 kilometers per hour. That's why we use the 72. It's the acceleration in this instant of time. It's not the change in acceleration that is asked for. It's the acceleration once the velocity of 72 kilometers per hour was reached. Okay.
Thank you, Professor.
Professor, what do you take the magnitude of the acceleration here?
Because it was asked for the acceleration. It wasn't asked for the tangential component nor for the normal component, but it was asked for the acceleration itself. And that's why we had to find the absolute acceleration. Vector addition.
So this is for 72 kilometers per hour?
Yes.
Okay.
The unit radians per square second or 1 per square second is the same. Okay.
Okay.
Okay. There are no more questions. I would.
Can you explain how you calculated the alpha again?
The alpha?
I mean the angle.
The phi or the alpha?
The phi. Yeah.
Well, I used this equation here. Then phi is 0. Well, you actually just have to read the equations from here. That's this equation. Phi is 0. Then omega 0. You can find here. Substitute this for omega. V over R times T. And it's this here. Omega. And then for alpha, I substituted this part right here.
I have a question.
Yes.
When we are solving for the first question, our angular acceleration, we got it in 2.10 raised to minus 3, 1 per second square, which is in degrees and not in rad per second square. But while we are calculating for the second question, our final answer is in rads and not in degree. How come?
We never use degrees. It's always radians.
But for the first question, it was
here
just in degrees. Yeah.
Well, that's not degrees. That's also radians per square second. That's what I just said. Radians per square second is identical to 1 per square second.
Okay.
But it's not 1 per square second. It's not degrees per square second. There is no angle in this equation. No, there cannot be degrees per square second.
I'm a professor.
Yes.
For phi, why did we take the phi 0 plus omega t plus alpha t square? What if someone use a formula only for phi is equal to omega t?
Sorry, I didn't understand your question.
Why did we use this long formula? What if someone used only phi is equal to omega t?
Phi is square root of. Are you
Phi is
talking
equal
about
to
this equation?
Yes.
Why we use this?
Hmm.
Because we wanted to compute the angle. So we had to find an equation for the angle. And then we simply look in the formulary. We have a circular motion. And then we have a look, okay, circular motion, how can I compute the angle? Oh, there it is. How can I compute the angle? That's my angle. And there's the equation for it. So I used it. You don't have to memorize equations or invent equations or something like that. All the equations you need are in your formulary. You just have to look them up. And the biggest difficulty might be finding the correct equation. But so far, we are still in chapter 1.2, circular motion, and there are only these few equations that we have available. And so this is the best to use
Yes,
for
exactly,
us.
Professor. My question is how to choose a formula, because phi is also equal to omega t.
I'm sorry, it's really difficult to understand you. How did I do what?
How to choose the right formula?
How to choose? Well, I need an angle. So where do I have an equation for the angle? Well, I have this one. They have to solve an integral, and I don't know omega as time-dependent variable, so I cannot use this equation. So my only other choice is this equation right here. Because here in this equation, I can compute omega, here alpha, here the time. They don't help. I want phi, I want the angle. Then I have to use the equation for the angle. And this, always the first equations are our standard equations. And then we know that this is 0. We can substitute this value. We have already computed this value. So there's no other option I have.
All right, thank you.
Okay. Okay. Let's go back to the script on the next page. Okay, because so far we are only able to discuss the simple forms of motion, either rectilinear motion, like the stone being dropped, or the circular motion, like the car driving through a curve. But in many situations, we do not have these simple types of motion. We have a motion that is somewhere in between, like a general motion. Okay, and now the most important thing you have to understand in chapter 1 is what we will do now. You have to understand how to describe a general motion. And general motion means we have some arbitrary path, for example, like this. And then we have our point mass moving along this path. We need a reference point to describe this mass, like the center of the circle in the previous chapter. And here in this case, we are like the person standing outside watching the object, the point mass, move. And then again, we always have a velocity tangential on the path, and we have normal and tangential acceleration, which sums up to an absolute acceleration, which may point, I don't know, maybe here. Okay, it's just a very simple. So without any numbers, any specific values. So again, for the general motion, we need the position, radius r, vector r, sorry, the velocity v, and the acceleration a. And depending on our specific situation, we might have to choose a different coordinate system. Right now, we are only using Cartesian coordinate systems, and we will do this throughout the whole semester. But of course, there are other problems where it might be helpful to change the coordinate system to a polar cylindrical coordinate system or whatever, okay? But for us, we are only using Cartesian coordinate systems. So now let's describe a point performing a general motion. For this, let's assume we have a robot arm. Yeah? So two rods that are connected by a joint and then fixed somewhere. So this is rod number 1, our joint, and rod number 2. And we want to describe the motion of this point here. Now, both rods are moving, are rotating about the joint. Now, let's assume they rotate clockwise. So some point later in time, this first rod might be here. And if this would be a stiff connection, a rigid connection, the second rod would be here maybe. But since it's not, they're connected by a joint, it moved a little bit further, and then it might be here. Oh wait, our red point P. So, and now we want to mathematically describe how our point P moved from the starting position, time t, to the second position sometime later in time, t plus dt. Okay, and to be able to do that, we have to break down this general motion into our simple forms of motion, because we are only able to describe circular motions and rectilinear motions. We do not have any equations to describe general motions. So we have to detect, we have to find the simple forms of motion. So what types of motion do we see? We see a rotation of the first rod, and it rotates with angular velocity in this direction, omega. And now, since this is our first motion, the motion I will detect when I'm, for example, when I'm standing on the hinge support and I'm looking at the system, I will see the pure rotational motion of this rod, and this is our leading motion. Index L stands for leading motion. And due to this leading motion, our point P, assuming that we have a rigid connection, there's no joint, our point P moves over here. That is dRL, the change in position due to the leading motion.
Excuse me, Professor?
Yes.
This leading motion became a leading motion because of where you were standing? I mean...
Yes, first of all, we'll have another example, or I will explain it on a different example again, but imagine this person, purple person, leading person, is standing outside of the system. This person is not moving, okay? And this not moving observer is looking for a simple form of motion. And the only simple form of motion he can see is this pure rotation of the rod. Now I'm able to describe this pure rotation of the rod, assuming that the connection here is stiff. but it's not. And that's why I have to step onto my system and I have to move with my leading rotation. Now I have a second observer. And what this person moving along with this joint sees is the pure rotation of the second rod, omega r. R for relative. Since the person moves relative to the leading motion, it's a moving observer. Purple is a non-moving observer. And what this person sees is this change in position. D, R, R. And of course, he also sees the change in angle, D, phi, R. Now combining these two, standing or non-moving observer and moving observer, leading and relative motion, when I combine the information that these two people here observe and are able to describe mathematically, then I'm able to describe the absolute motion. And the absolute motion is the change in position from the red point to the other red point, dr. Red, no index, that's the absolute motion. And now, knowing this, we can write this equation as a vector equation. And with this vector equation, we are able to describe the change in motion for the position, the velocity, and the acceleration. I will write it once for the position using the colors. dr, our absolute change in position, can be found by change due to the leading motion plus the change due to the relative motion. This equation is true for position, velocity, and acceleration. I will state below the same equation. Now I will not use the colors, but the indices, of course, and then you know what colors are referred to. For the velocity, it's again leading motion plus relative motion, and then we obtain the absolute velocity. So again, you have to stand next to your system, not on a moving part of your system. You're standing next to your system, you're looking at your system, and then you have to think, which of these motions can I describe as rectilinear or circular motion? Once you identify this motion, you can describe this motion mathematically. Then you step on your object that performs this simple type of motion, rectilinear or circular motion. You step on this object, and again, you have to think, what type of motion, what kind of simple motion can I describe from here, like the green person, circular or rectilinear? And this is your relative motion, and you can describe this motion mathematically with the equations from the previous chapters. Now, if you do a vector addition of the variables that you derived, velocities, for example, of leading and relative motion, then you will find the absolute motion. And that's all you need to do. That's all you have to do. You have to identify the problem, okay? You have to understand the motion of your problem from the figure given. And once you were able to do that, you describe rectilinear motion, circular motion, really simple equations, all stated on the first page of your formulary. You do the vector addition, not a simple sum, not a simple addition, it's a vector addition. But we will practice this in the next weeks, and then you obtain your result. Similar for the acceleration. Um,
Excuse me, Professor.
yes.
I have a question. So like in the first semester, we did this, what's it called, in physics, general relativity. Is it the similar concept? Because we had two systems, one was static, the other one was moving, and it had to do something with the difference in light. Or is this not?
Yeah, well, could be. I don't know what you did with these systems. If you only describe the system relative to your motion, then that's not identical, because here we want to describe the absolute motion. So from the point of view of the outside observer.
Yeah, I think it was similar to this, because it had two systems in it. One was a still observer and one was in the spaceship.
Yeah, well, could be.
Okay, thank you.
Well, Doppler effect is something different.
Okay.
So,
maybe I'm wrong. Yes.
Yeah. Yeah, we will also do these disk problems. So, but it's in Germany, it's a person walking on a roundabout, on a merry-go-round, and not a rat on a disk. Okay, now we still need the accelerations. We will discuss this on Monday, at the beginning of the class, just a few minutes, 5 to 10 minutes, and then we will apply these equations to several problems. I will solve one for you, and then you will have time to solve various problems on your own, and then please ask me for help and etc.
Ma'am, can you please scroll up a little bit? Thank you.
Yep. Okay.
Professor, I'm
for
really
today-
sorry, but I understand what you're writing and what you're talking about. But however, I was wondering if you could give more details in your solution, like how you derive
We
certain
haven't solved,
formula.
and well, the first two problems we solved so far, there's no more details I can give, because it's just no more equations. Or what details are you missing in the today's
Maybe like some
exercises?
formulas where you take from the formula sheet and show us how you actually plug those things in.
Well, that's what I did, didn't I? If I
Some-
look at the question
you, like,
1.4,
skip to
what
the
what
thing.
is missing here for you? The numbers?
Nah, just some simple formula, like just some stuff like wait.
Well, I can write here page 1 formulary, something like that. Well, it's not. I mean, I rearranged the equations and I stated all the only thing I did not do was inserting the numbers, but they are all stated here. So if you have problems inserting the numbers, I can write the numbers as well, but you have to use your calculator on your own.
that is
So,
okay.
so it's not. It's no more than that. We have the radius given. We have the angle here. We substitute it, multiply, and we obtain 175. So there are no more. I don't know what you're missing. So if you have, of course, you can ask if there are steps missing, but I think there are all the steps. I did not make more steps on my paper solution.
Okay, thank you, Professor.
Yep.
I have a question to the solution, actually. I
Yes.
want to ask that before. So it says that the car is accelerating constantly.
Yes.
So why do we get a different acceleration at the end if the acceleration was constant in the first place?
No, it accelerates constantly, so it changes. But no, no, wait. It accelerates constantly in a plane curve. That means that it's not a time-dependent variable. But of course, our car moves along. Let's draw another figure. It moves along a circular path. Okay, and alpha is constant. But then still tangential and normal, well, tangential, but normal acceleration changes dependent on the change of the velocity. Let's do another color. This stays constant throughout the whole time, since alpha is constant, our constant acceleration of the car. But this part, the normal acceleration, depends on the velocity, the change in direction, what we did at the beginning of this class. And that changes since our magnitude of the length of the vector changes.
Okay, yeah, understood now.
Okay.
So in simpler words, the tangential acceleration is the property of the car or the motor or whatever
The
driving?
property of the circular motion, of the circular acceleration, angular acceleration. So the
Is it
tangential
not
goes
the
with alpha.
normal? Is it not the normal acceleration, which is because that's changing 0.5, like tangential is staying the same, is staying constant. And
Yes. Oh, I misunderstood your question. I thought you were referring at what does not change. So tangential doesn't change.
Yeah. So
but-
that's the property of the car, and
Yes.
N normal one is the property of the motion itself.
Yes, you can probably say it like this.
Yeah. Okay. Okay. Thank you.
Yep. You're welcome. Okay,
Professor,
yes.
one last topic that if you go to our lecture sheets, page number 5, there is also another like formulary, it's simple formulary. Bt is equal to R d phi by dt. Here it also returns me an angle. Isn't that angle the same that we have derived from this big formula? Like mine is 0.8, but yours answer is like 0.72 or something. So is that wrong to use that?
I don't quite understand which formula you're referring at.
Lecture sheet page number 5 at first formula. Yes. No. That was the first formula. Page number 5.
Oh.
5. Yeah, here the first formula. No, the formula that is typed. Vt is equal to R d phi by dt.
Yes, but that's just for rectilinear motion.
No, the velocity, but it also gives me the angle, and here the velocity that has been given me. Isn't it the rectilinear velocity?
A is equal to dv dt does not give you an angle.
No, the first one, Vt is equal to R d phi by dt. That one.
Maybe can we discuss this on Monday, because I'm have another appointment in a few minutes. Okay. Just I don't know if you're here in Schweinfurt, then you just show me what you mean on your paper, or we discuss it online.
Excuse me, Professor.
Yes.
Can you please upload the written script of yours?
Can you talk a little bit louder, please?
Can you please upload the written script of yours on e-learning?
No, not yet, because and also I don't think that it really helps, because if you have a look at my script, then I'm always writing there, referring to your questions and all stuff, and it will just be really confusing for you. So I recommend to really write on your own, but maybe later on. But I don't know if I have the chance to clean it first. Okay, then. Have a nice weekend and see you on Monday. And I hope a lot of you will show up in person, but I think it will really help you a lot.
So wait, Professor, just to get this clear, the only class that's on like present, like face to face, is on Monday at 11.
Yes, because 2/3 of your class of third semester students voted for online classes, and that's why we have to do it online. I don't think it's a good option, but anyways,
So I saying there is still a face-to-face class.
There's one face-to-face class and 2 online classes. Because I think for the students who are in Schweinfurt, it will help them participate in online classes. And on Monday you choose online or offline, and on Friday it's only online.
But on Monday we only need to select one, right? We don't have to attend both.
No, yes, one of them.
Oh, okay, all right. Okay, thank you.
Okay,